All right, welcome back to System Software. Looks like mostly everybody's here. So let's take a look at how far we've come so far. Let's see if I can turn this down. Testing, testing. Is that a little better? Can anyone not hear me? I don't know how you'd answer, but. Okay, so we're in the third week of System Software. We've looked at the programming environment, looked at the development environment. Hopefully, almost everyone's got their virtual machine set up that we're going to use for the class. I know there's a few people still having issues. Please continue to come to office hours, ask on ed discussions, ask in labs, and we'll make sure that you're set up, or we'll have an alternative for you. We looked at the overview of the course. So now we're going to get into some of the technical meat of how actually compilers are written. So today we're going to look at how we can actually write our own compiler, a very small toy compiler for just doing simple arithmetic operations. And I'll walk through that today, and then you'll have an assignment where you just hand write or hand manually enter the source code of this compiler. It's the only time that I think probably in your whole education you'll be able to just copy code, but the point of it is not to write the compiler yourself, but to get used to the programming environment, to get used to what a compiler looks like, just to give you practice. So you have to write it yourself. You can't just cut and paste somebody else's. That would be cheating in this case. But I've given you pictures of my terminal window that you can use as a guide to write your compiler. But I'll go into that today. So before we get started, are there any questions about last time? Everyone good on using the command prompt? Hopefully there's a learning curve there. There's a sort of long learning curve to doing that, but once you, it'll be muscle memory once you start typing the commands over and over, and you'll be faster than dragging and dropping and moving a mouse for at least the tasks in this class. Okay, so let's build a compiler today. So just to review, a compiler is a language translator. We talked about a little bit in the first class. And one way to think of this is that it bridges human languages, or human-friendly languages, that machines will not process. They're just text files, which is what humans like to deal with, and machine code, which is tricky to deal with. If you were programming a personal computer like 40 years ago, you may be flipping switches to enter each bit of each instruction on a machine with no screen, with no keyboard. And so having a text-based language that is much easier for humans to process is really useful, and it's the compiler that bridges the two. So today we're going to write a compiler that will work for simple arithmetic expressions. We're just going to do addition, subtraction, multiplication, and division in a text file, and we're going to translate that into Intel assembly and just print out the results. So here's an example of what our input and output to our compiler will be. So remember, there are three languages that you have to be thinking about whenever you're programming your compiler. You've got the input language, you have the output language, and what's the third language you have to worry about? Yeah. The language you're writing the compiler in. So those all might be three different languages. And as you'll notice once you start implementing the compiler, to me that's the hardest part. You have to separate these three languages and realize that your input of your program is a program itself, not like some number that you're trying to compute. Okay, so the input language that we're do today for our toy compiler looks like this input program. It's going to be integer digits, the symbols for the arithmetic operators, and semicolons. And the output program is going to look like this. So someone who's seen Intel assembly before? Not much, right? I think you probably learned MIPS, maybe? MIPS? So this is Intel's assembly. It's maybe a little less intuitive. But similar idea to MIPS. All this is doing is it's moving the immediate value, the constant 1, into this register. This is the EAX register. And then we're moving a different immediate value into the EBX register. And then we're running add. And in this version of Intel assembly, this is the AT&T syntax. The destination is on the right. So this is adding EAX and EBX and storing the result in EAX. So you're not going to have to, once we actually get to the compiler, you're not going to have to know too much Intel assembly. I don't know very much Intel assembly. I'll give you basically the patterns and all the instructions you need. We're going to use a very restricted set of instructions. But that's all this is doing. Same here for the subtraction. So you can see that the goal of our compiler is to take this text, which the processor is not going to do anything for you. It's probably just going to error out with an invalid opcode or something. And we're going to translate that line into these 3 Intel assembly instructions. Questions about this? And so this is effectively what GCC does when you write your C program. It's translating that .c file into assembly code that looks very much like this. Questions? Okay. So what would you do? So if you were given this task, you're at work and somebody says, yeah, we're having a hard time programming this processor, we want to make it easier. We just want to have a text file with arithmetic operations. How would you do that translation? Any takers on how you might attempt to do this? Yeah.
Read in a line until the semicolon, find the plus, and put either half into the move L1, move L5, set 1 and 5, whatever.
Okay, so something like you've probably learned string processing algorithms in CS1, CS2. So you'd step through each character, look for the semicolon, and then say, okay, if I have an integer here, or a digit, you can check if it's a digit, then I output the move instruction. If I see the plus, I output the arithmetic instruction. Yeah?
You could also go about it kind of like translating infix expressions into postfix expressions.
Okay. So that's interesting. So who's done the infix to postfix conversion or something like it? Is this like CS1, CS2, you do this? CS1? Okay, that's good, because that's actually kind of an instance of doing language processing. What's the data structure you use to make that possible? A stack, right? Use a stack. A stack holds the operands while you look for the operator, or vice versa. You know, if you're doing, what was it? Infix to, what did you do? Infix to postfix? So that holds the operands for you while you find the entire expression, and then once you've seen the whole expression, you can spit out the new version of it. It's actually going to be very similar for this compiler. This notion of a stack is used to store nested constructs. And we'll see that once we actually get to the larger compiler, and next week when we look at a different version of the toy compiler. But that's exactly what we're going to be doing. A stack is the critical piece for doing this language recognition. Okay, good. So I think that those answers are pretty good. That's the general idea. We're just going to be looking for these ASCII characters, because remember, the input language is just text. There's no machine operations or numbers here. We're going to try to recognize when we see the plus symbol or the 1 symbol. And we're going to, once we see those, we're just going to say, okay, if I see that, then spit out the assembly code. Okay, so as I mentioned at the beginning of class, there'll be an assignment for this. I'm going to give you, I'll walk through it probably in the second half of the lecture. I'm going to give you a source code repository that has some of the C files replaced with images of what the compiler looks like, and then you'll just hand type it out in your own C file, and you'll be able to build and run and have your own working complete compiler for this arithmetic language. So just to be clear again, follow along means typing it out yourself, no help from others. You shouldn't need help if you can type and read an image. Shouldn't need any help. I know it's very easy to just copy files. Don't do that. That would be cheating if you do that for this example. Just type it out. It's not that hard. It won't take you that long. And this is the only time in this course, and probably ever, that you can just like copy code. Because the exercise is not to figure out how to write it, but it's to make sure that you can actually use the setup and that you get practice looking at what a real compiler, a real toy compiler, looks like in code. Okay, just as a little refresher, this is the phases of a compiler. So the input is just characters, text characters, which I think you've all done string processing, so it's just a sequence, it's just an array, effectively, of characters. The first step that we do is lexical analysis. We basically use regular expressions in order to recognize individual words in this language. So in our toy compiler, the words are just plus symbols, digits, and semicolons. And that gives us this stream of tokens. So we go from an array or a list or a stream of characters into a stream of tokens. So you can see here there's like, 20 characters, 25 characters here. And we go down to just 7 tokens. So we've grouped together all of the characters that represent one word in our language. Syntax analysis is where we get this hierarchical structure. So when you did that infix to postfix exercise, you were capturing, it's a shallow structure, but you were capturing the structure of infix. You're capturing the fact that you have a plus symbol in the middle and you have 2 other expressions on either side. And those can be nested. So syntax analysis just recognizes and captures this hierarchical structure of the programming language. Semantic analysis checks that you're using the right types so that you're not, say, trying to add an integer to a struct in C. Intermediate code generation. We won't use this in this class, but in industrial strength compilers, instead of translating immediately to a machine code, they'll translate to a kind of abstract machine code that looks like lots of different machines. And the purpose of this is just an engineering choice. If you want to retarget the compiler to different architectures, it's easier to go from a simpler language than from C. We've got optimization, which we're also not going to do in this class. If you're interested in that, take the graduate compilers class. These are techniques that will automatically improve the code. So finding when, instead of doing, say, multiply by 2, you do shift by 1. And then finally, we have code generation, actually producing the machine code. So I went over this already, so this is just lexing, parsing, type checking, intermediate code generation. Here's an example of a industrial compiler framework. LLVM is the name of an intermediate representation. And so this illustrates the benefit of having an intermediate language instead of compiling directly to machine code. So if we've got several languages that we want to compile, so C, C++, Python, Scala, and lots of architectures that we want to target, MIPS, Intel, PowerPC. If we had to write one compiler for each input and output language, well, there's like 5 languages here, 5 machines here. How many compilers would we need? Like 25 compilers. Here, we only have to write 5 front ends and 5 back ends. So, 5 halves of a compiler and another 5 halves of a compiler. So it just saves energy. It's just engineering design to have an intermediate language. So here's an example of what optimizing compilers do. Here's a C program that you might write because you want to have variable names so that you don't have magic numbers everywhere. In this program, we're assigning 10 to x. We're assigning y to 1 plus x. We're checking if y is greater than 7 and printing if it is. So if we were to naively translate to this assembly, we'd have a memory load here potentially, or memories move here. We might have another memory access for x and an arithmetic instruction. We'd have to do some conditional test and a branch and print. But how can we improve this code to have fewer instructions or faster instructions in assembly? Yeah.
Get rid of y.
You can get rid of y. Why can you get rid of y?
It's just like storing input stuff.
Well, so okay, if we get rid of y, so like we get rid of y here, right? What would we this would be not syntactical if we just delete this. So what would we replace it with if we get rid of y? Yeah.
When you replace the y greater than 7 with x greater than 7, and then the y with the 1 plus x.
So you're saying replace y with x.
Replace the other y with 1 plus x.
Okay, that actually might work in this case, right? Okay, so replace y with x, so yeah.
Can you just replace y with 11?
So one is you can replace y with 11, because no matter how many times you run this program, no matter what inputs you give it, y is always going to be 11, right? Yeah, go ahead.
Instead of checking y greater than 7, we do x greater than 6.
Could do that too. So you can. So I'm hearing lots of different substitutions. Yeah, go ahead.
Replace the whole thing with printf.
Replace the whole thing with printf 11. Or what were you going to say? Same thing. So so we have lots of options here. So we eliminate x or eliminate y rather. But if you want to go really, really far, you can observe that x is always going to be 10 in every execution of the program. Y is always going to be 11 in every execution of the program. 11 greater than 7 is always going to be true in every execution of the program. And print 11 is always going to happen in every execution of the program. So truly, you could actually just replace this entire program with just print 11. And optimizing compilers can actually do this. They're able to do this. They're clever enough to do this. But if you're interested in optimization, read the Dragon book or read a text on it, or take the graduate course, because we'll go a lot more into how this optimization actually works. But the compiler that we write, it's much easier to write a compiler that doesn't optimize, that just does very naive, systematic translations from the input language. And so if you actually want to see, and I can actually, let's see, yeah, let me show what, how you can actually have GCC do the actual compilation for you. So let me take a example program here. Okay, just a simple hello world program. And if you want to see how, so GCC-C will just give you the object file. It won't do any linking, which I think we covered last time. So here's my hello.o. If you want to see the output of the compiler in assembly code, in assembly text file, do -S. And so now our C program, and instead of a .o file, it'll give you a .s file. Here's what our assembly version of this program looks like. And actually, why don't we take a look at whether it will actually optimize the program we were talking about. So if I take this program here, so there's our program on the left, and let's see if it can actually, whoops, I didn't clear the variables. That was a rookie mistake, so it's just complaining about standard I/O, but it'll include it anyway for us. So it's a little hard to see with all of the all the stuff going on here, But here it is. Oh, actually, so it didn't optimize it away. There's the 7. There's the 1. Let's see what happens if we print out y. Oops. Turn up the optimization level. So there, as you can see, the 11 here. So it's doing some of the optimization here. It looks like yeah. So it's optimized away the branch as well. So there's no branch here either. But anyway, without going into the details of all the code, it's doing the optimization. It's actually computing 1 plus 10 in the compiler before it actually translates. Why is this? Okay. So that's how you can actually have GCC show you the machine code in the assembly format. Okay, so as I said, it takes a list of arithmetic operations, produces Intel assembly, and then once we have that Intel assembly, we can use GCC to assemble and link it into an executable for us. So here's a fuller version that includes the call to the print statement. So this is the same code we saw before when we translated 1 plus 5. And our compiler, just so we can see output from running the compile program. I've also added a call to printf. That's all this code is doing. So this is the return value. This is the passing of the parameter. We'll see this more when we look at code generation. And this is the call to the print statement. But that's all this code is doing. So here's the computation of 1 plus 5 and the call to printf. So that's the output we want to see from our toy compiler. Questions so far? Okay. Okay, so let's get into actually specifying this compiler. So we had a loose, intuitive notion of what this compiler is supposed to be. We had some ideas about how to might implement it. So let's make this a little more thorough and systematic. So the first question is, what is our input? What is our input really? So what do we really mean by arithmetic expressions? If I open up a text file, if I open up a text file like this, and I start writing expressions, what does this input actually look like to the machine? So here's my example toy program. If I print it out on the console, it looks like 1 plus 3. But what's this representation actually look like when it's stored on the machine? So how do machines store information? Or at least the current machines we have? In binary. So there's literal like voltages that are high and low that represent that we call 1 and 0, and the hardware is designed to be able to read those high and low signals to do operations. And when they're stored on a flash drive or a hard drive, there's some way to record 2 states for each data value. And it's the same thing with text. So even though this looks like text on the screen, if we look at the actual binary of this, which we can do using this command called od, which I think I showed last time. So this shows in hex what the information in this example.toy file looks like in hex as numbers. So not super intuitive. And okay, so I guess first of all, is the number 1 here? Is the number 3 here? It's somewhere, right? There's a number 1 in hex. There's number 3s. It doesn't quite look like 1 plus 3, though. There's certainly no plus. So does anyone know what these numbers represent? Or what these numbers are? Yeah. Yeah, so this is ASCII code. So who's heard of ASCII? Did you guys learn about ASCII? Okay, good. So when you were doing like string processing, each character was actually assigned a number, and that's how these text files were stored. You can look at the table so this is just a convention. There's no one way to represent letters with numbers in the machine. So in our current current machines, we use binary numbers to store our data. And in order to be able to store textual data, like Latin characters and numbers, Arabic numerals, standards bodies have just decided that, well, if you want to represent the number 0, then you can do that in hex with 30 in hex, or 48 in decimal. So each of these symbols that are printable in our console, plus, comma, minus, these are all assigned a number. And so ASCII isn't the only table, that's the only assignment of numbers and symbols. There's also Ipsodic, the old IBM scheme. There's Unicode, which expands the number of symbols that can be represented. So if we were to actually look at the actual input to our compiler, and we wanted to have text files, this is what our compiler and our machine is looking at. It's not looking at these symbols. Now in C, you have the char type, but if you try to actually print out the raw data that's backing that character, you would see something like this, depending on how you're formatting it. Okay, so that's the actual input to our compiler. It's not the number 1, the symbol plus. It's just ASCII characters. And we have a lot of questions about the design of our input. So do we allow spaces? Spaces are also, even though they look like there's nothing on the screen when I have a space. So for instance, if I type hello world, correct, spelled correctly, then you'll see even this space. Well, it's a little hard to see here. So let me do the C representation. Well, okay, it shows the space. HELLO. So there is a character for space here. The ASCII table has a character for space and like new line. So even empty space, like new lines, tabs, these are also given a special ASCII character. So even though it looks like the console just prints nothing and instead moves the cursor to for the space, there's still a character representing that. So if we were to design our input to allow for space, we'd actually have to worry about that in our compiler. We have to look for space. We can't just take for granted that it's not there. And same thing with a new line. So in this ASCII table, this is why you type \n in C, because \n is a real character. It's called a non-printable character. There's no symbol to display, but it controls the cursor to move the cursor to a new line, which is why you get a new line when you print out on the console your Hello World program with the \n. So our compiler has to worry about all of these aspects of it. We take it for granted when we look at a text file that, oh, we just hit enter and there's space here. But that's actually encoded in the input program in ASCII. And so our compiler, when we write our toy compiler, we have to account for that. We have to look for those special characters. Okay, so in contrast, since we're doing Intel assembly on the processor, how are those numbers represented in the machine for, say, an Intel processor, or any, most processors that we have on the market? How are those numbers represented on the machine? You all took computer organization, right? Or is this too easy of a question? Too hard of a question? Yeah. The address, well, it does actually depend. Depends on, if you have floating point or integers or signed or unsigned integers. So pick one. I mean, pick one of them. Registers are where they're stored. So if I want to store the number 1 in a register on my processor, so it's all binary. So what does the binary look like for the number 1? Say, unsigned. What's that? I mean, yeah, it'd be 0, 0. What about 2? How do we represent 2? 1, 0. Yeah, so all of this is binary. So the input ASCII is binary. The output is going to be, in machine code, is going to be binary. But on the machine uses the binary number representation for all of this. So we're effectively going to be converting these numbers here. So we've got the ASCII symbols for these numbers here, 0 through 9, which have the decimal values here. We're going to be converting them, ultimately, through the help of the assembler, into, here are the numbers here. We're going to converting these symbols, which have these numbers when stored in binary. We're going to be converting them to the machine representation of these numbers, ultimately through our assembler. Okay, so that's our input and output. So let's give some informal syntax of what this program looks like. So just like when you looked at your infix to postfix translation, you had to capture the nested structure of those input expressions, those infix expressions. So in our toy compiler, we're going to define the syntax, the set of valid legal inputs to our program, as being a list of statements. So a list of 1 plus 3 semicolon, and then 2 plus 7 semicolon. Each of those is one statement. A list of statements contains a statement followed by another list of statements. And then a statement itself contains one expression followed by a semicolon. An expression contains a number, and then an operator, and then a number. A number this is where we get to our actual representation in the input. A number is a single ASCII code for a digit, so we're only going to allow single character, single digit numbers. And an operator is an ASCII code for one of these 4 symbols. So I say / here because ASCII has no notion of what division is. We could use any symbol we want for division. We could use the plus symbol and then translate it into division. There's nothing intrinsic about the ASCII code as it relates to the meaning that we want for our input. Okay, so syntax tells us what inputs are valid to our program, what textual inputs are valid. The semantics tells us what it means, how it should be translated. And so for our compiler, we're going to assume that the ASCII codes for digits means machine integers. We're going to assume that, define that each ASCII code for these operators corresponds to some assembly instruction for that corresponding operation that we want to do. So the plus sign is going to be used to generate an addition instruction, minus for a subtraction instruction, star for multiplication, / for divide. So this probably seems obvious, right? These are like the conventional ASCII codes we use. But when we write our compiler, there's nothing helping us to automatically figure out that a minus sign should mean subtraction. It's our compiler that's going to be implementing that semantics, implementing the meaning of those symbols. And finally, each complete statement computes the result and prints it to console using printf. All right, questions about the semantics of our compiler? So pretty straightforward, right? Okay, so I went through this already. The text files are just bytes. So recall that in our compiler, we first need to process the text input and find each of the words in our language. So our Lexer is going to take in all of these individual characters, and it's going to spit out what part of the language that we've seen that the Lexer has read. And so there's only 4 different tokens in our language, only 4 different types of words in our language. We have numbers, which are a single digit, we have an operator, and we have a semicolon. So those are only the 3 types of words that we need to worry about in our language. Now each one of these has several variations, so there's 10 different numbers, 10 different ASCII characters for numbers. There's 4 different operators, there's 1 different semicolon. But there's only 3 different types of words in our language. So think like noun. There's lots of different nouns, but when you look at where a noun can be used, it has a restricted place that it can be used, and there's a finite set of those nouns for the type of word. So just like in grammar, we assign names to the types of symbols that we have, even though nobody ever types the word number in the input. Our Lexer is going to do the job of taking ASCII code and figuring out which word, which token, that it recognized in the input. Questions about this? So the toy compiler code will have functions for creating each of these tokens for you. So it'll turn that ASCII file into a list of tokens. So once it identifies each word in the input, it will create a data structure so that our later phases, so that when we go to say, convert 1 into a move instruction, we can just check, okay, do we have a number? Okay, if we have a number, then we know we need to make a move instruction rather than having to look for each character that the number could possibly comprise. So I've given you a library of these 4 functions that will create a data structure for you to hold the word that we've recognized from the input. Create number, create operator, create semicolon, and create end token. And then our Lex algorithm will be pretty short. All it's going to do, it's going to loop over each character in the input one at a time. It's going to check what kind of ASCII character it is. If it's a digit, then it'll say, all right, I've seen a number, so I'll create a number token. If I've seen an operator, one of our 4 operators, just literally do ASCII character matching in C. And then once it sees each type of token, it will call the create function corresponding to that token and return it and give you this list of tokens instead of individual ASCII characters. So we'll see how this process can be generalized with finite state machines. So if you haven't taken discrete yet, you'll see this in discrete. We'll just cover it just enough to learn how to build our compiler. But it's really just a way to generalize this lexing process, identifying patterns in strings. And we'll cover it later in lecture 6. So let me actually diagram this to give you a little roadmap to what our toy compiler will look like. So we'll have some input that has the sequence of ASCII characters. This will go into our Lexer, which will produce a sequence of tokens. So for this input program, what would the sequence of tokens look like for our Lexer? Given those, so remember there were only 4 different there were only 4 different tokens, number, operator, semicolon. So what would the token stream look like coming out of the Lexer? So it's the first token that we would recognize. Number. And the next token we'd recognize, and that number would be, ASCII character 1. Well, the next token we recognize? Operator. And the actual value of that would be plus. And the next token? Number. All right, good. You guys are great Lexers. And so we're going to write this algorithm. That's what this Lexer algorithm is going to do. It's going to take this input and basically figure out the type of word we've seen from the input. This is much easier when you have single digit or single character words in your language. But once we get to our bigger language, Simple C, and we've got, a number can be multiple characters, you have space, you have keywords with multiple characters. This Lexer process is a little harder, but this is our toy compiler to make it easy. Each character or each token only has 1 character. Okay, and the next step in this is parsing. Who's done sentence diagramming in grammar school? I think they stopped doing this. A few people. All right. So the parser is basically an automated sentence diagramming tool. So just to go over sentence diagramming real quick. So if I so sentence diagramming just shows you how to break down a sentence into its individual parts. So we've got a sentence here, we've got subject, verb, object. In this case, the subject is a noun, the verb is a verb phrase, I think it's called, goes to, and the object is another noun. And so you can break down language, express utterances in language into this hierarchical structure, this nested hierarchical structure that kind of in some linguistic theory restricts the possible inputs to only those that are valid in the input. So we'll go over grammars more. I think it's in lecture 7. We'll go into that in more detail. But this is what sentence diagramming looks like. You just have a single utterance in your language, like a sentence or a paragraph, maybe made up of multiple sentences. And it shows how the sentence breaks down into these grammatical parts. Our compiler is going to do the same thing with our programming language. So recall our informal syntax here. At our informal syntax, we had a program, a statement, a list, statement list, a statement, expression, number, operator. And it has this hierarchical nature to it. So we're going to break down this input here into a parse tree, a tree that's going to diagram our input. And so for this input program, 1 plus 3, semicolon, 4 star 7, we're going to break it down into a tree that looks like this. So a program consists of a single statement list, and a statement list consists of a statement followed by a statement list, and a statement consists of a number, an operator, and a number. Oh, sorry, actually it's expression. I forgot expression. So statement consists of an expression followed by a semicolon, and an expression consists of an, let me make this less janky here. So statement consists of an expression followed by a semicolon, And an expression consists of a number followed by an operator followed by a number. And our actual number here is 1 plus and 3. And then we've got yet another statement list on this side, which consists of a statement followed by a list. And this statement consists of an expression followed by a semicolon. That consists of a number followed by an operator followed by a number. And it was 4 star 7. And then this list is just empty list. So I'll just use a little symbol for empty list. So this is what the parser is going to do. It's going to turn this sequence of tokens from the input and diagram it so that we know exactly where the expressions are, where the statements are, and make sure that, first of all, it's a valid program, that we haven't put an operator without a right operand, or that we have other symbols that aren't valid in our program. And notice here that if we did a traversal of this tree, let me actually show if we did okay, who's done tree traversals? Post order, pre-order? I think everyone should do that, right? So looking at this tree, if you can read my terrible handwriting, what would a post order traversal of this tree look like? So recall that post order says, look at all the children first, then do the parent. So if we start from program, we'll look at all the children first. We see statement list. And then we recursively do all the children, starting with the left child. And then it has its own children, so we go, it's child. Okay, does someone want to take a stab? We'll talk about recursion more as well when we talk about parsing. Does someone want to take a stab at a post-order traversal of this tree? Yeah.
It's gonna be number, operator, number.
Just do the leaves. I mean, right, post-order traversal, just print the leaves, I guess. Print the leaves in a post-order traversal. Let's say that way.
You mean the one on the top or the one on the bottom?
The leaf node. So these are all the leaf nodes here.
That's 1, so it's 1 plus 3 and then semicolon.
1 plus 3 semicolon.
Yeah, and then statement, I guess.
So if we're only printing the leaves, then statement has children. So yeah, we'll go to statement. We'll print its children, and then we'll recursively print its children. So the next leaf that we'll print is 4. The next will be star. Next will be 7, and semicolon. So another way to look at it is, if you just read left to right, the leaves of this parse tree, it's just the input program, right? It's just the input. So the parser will take this input and create this superstructure that tells you all of the parts of speech, all of the syntax of this input. Questions? I know you may have questions about like how to do this or details of it. We'll do that when we talk about parsing. We'll formalize this a bit. But questions on this so far? So we've taken this input, we've identified all of the tokens, the types of words here, and then we've created this syntactic structure on top of it that tells us what's a statement, what's an expression. And then the next phase, we're not going to do optimization or type checking in this compiler. The way we're going to use this is we're going to take this tree that we've created and recursively traverse it. And as we traverse the tree, we're going to generate our assembly code. And we'll see that by having this tree, it'll make it much, much easier and much more systematic to generate our code. So for instance, if you were to just read these individual tokens one at a time and try to generate machine code, it might be a little tricky to do. So for instance, our machine code is going to do 2 move operations and then the plus operation, effectively postfix. And so if we just didn't know what the third operand was, we'd have to store something onto a stack, we'd have to hold on to it, find the plus, generate the machine code. If we don't see a semicolon then it's not a valid input, so we have to generate an error. The parse tree effectively captures this, all of this syntactic information about our input. And we'll see more when we talk about recursion, but it's basically a record of a series of recursive calls. Trees and recursion are like a one-to-one map. So anytime you have a recursive algorithm, even though it looks like you're calling the same function over and over, you can think of it as a tree of function calls. But we'll talk about that more when we get into recursion. Working with parse trees and working with language processing I hope it helped me better understand recursion. I hope it will help you as well. So what we're going to do when we traverse this tree is when we see that we have a valid statement, we know now that we need to generate we know that we're going to have an expression, and so in order to generate the assembly code for the expression in the statement, we can just look at the child tree. And whenever we have an expression, we know we're going to have a number followed by an operator followed by a number. So when we see expression, even without seeing the rest of the tree or the rest of the input, we know we're going to generate code. Sorry about that. We know we're going to have, as soon as we're on expression, we know we're going to have code that looks something like this. It's going to move something into EAX. It's going to move something else into EBX. And then there's going to be some operation here on EBX and EAX. So as soon as we see that expression, we know this is the pattern we're going to be generating. As soon as we see statement, we know we're going to just print whatever came from the expression followed by the code for printf. Kind of makes sense? So we don't actually have to look at the input characters anymore. We can look at the nodes of the tree, associate those with a code pattern, and then just look at the child nodes in order to fill out the pieces of that code pattern. So in order to print out the statement, we need to take whatever the expression gave us and just print it out before we do the printf. Whatever node and the number and operators were in the expression, we just take their return values and use those to fill in all of the pieces in our template. Sort of makes sense? So this is how language processing will work, and this is how our compiler will work. We construct this parse tree so we know each grammar construct that's being used, whether it's an if statement, whether it's a while loop. We associate a code pattern, an output like machine code pattern with each of those types of nodes. And then we just look at the children in order to fill in the pieces for that template. So you won't have to worry about how to work all this out. I've worked it all out for you. You'll just hand copy our toy compiler so you can get a feeling of how this works. In order to construct this tree, so I've given you, so we have the syntax. The syntax is pretty straightforward. It's just a statement list. Statement list contains a statement followed by another list of statements, statement, and an expression. And I've given you an API to actually construct this parse tree. So just like the Lexer will give you a stream of tokens, token data structures, the parser will take those tokens in and it'll construct a parse tree. And each time you see one piece of the input, whether it's a statement or an expression, we'll call one of these creation nodes, creation functions in order to create a node in the tree. So this is the interface between the parser and the Lexer. So the parser is just asking the Lexer, hey, give me the next token, give me the next token. And then Lex is the function that gets called, which just says next token, next token. And the look ahead is how we're going to be able to figure out which construct we're trying to parse. We'll talk about more of that, how actual parsing algorithms work in a couple of weeks. But this is how the parser and the Lexer work together. And yeah, as I said, we'll talk about a formal way to generalize this notion of parsing in a few weeks. Okay, so I went over this pretty much already. You'll look at each node in the tree, and we'll associate it with this assembly code pattern. And we'll just recursively traverse the tree, printing out the assembly. And if we've designed everything correctly and made sure all the pieces compose together properly, we'll have a valid assembly program that does exactly what our input program is supposed to do. So one way to look at this is that the compiler is defining the meaning of your input program. The input program is just literally ASCII text. It has no computational meaning by itself. You know, if a tree falls in the woods, nobody's there to hear it, doesn't make a sound. If symbols are on a page but nobody can interpret what they mean, do they have meaning? We as humans, we've all learned math and arithmetic, so we're interpreting those symbols. But there aren't just Arabic Hindu numerals. There are lots of numerals. There are Chinese numerals. There are Sumerian numerals that you may not know about. But they're different symbols, but they have the same meaning. And they have that meaning because there are people or machines that can process those inputs and give you some output. So our compiler is a machine that will take these symbols, translate them into another language, and in that process of translation, it's effectively ascribing meaning to that input. And to help you do this, I've given you a little API that will help walk the tree. So I've called these gen code. So once we have that parse tree, you'll call the code gen function, and there'll be 3 functions in there, one for each construct in the language: statement, list, statement, and expression. And inside of each of those, you'll have basically print statements that will just print out assembly code. And these are the assembly code instructions. Okay, questions so far on kind of abstractly? I know we haven't looked at the code yet. We haven't actually run the compiler. But any questions on what the task is for this toy compiler? Okay. All right, so I think this is a good time to break. I've shown you the overview of what our toy compiler is going to do, and then let's go into actually coding. I'll show you how to run it, how to download it, and then we'll actually code it up. So let's take a 10-minute break, come back at 10:45, and yeah, we'll go from there. Okay, everyone, welcome back. All right, so let's go over how to actually get this assignment and turn it in, run it, and then I'll do some live coding, starting to actually walk through the implementation. Okay, so if you're on web courses, there's a link here to generate the repository for this. It's also in the assignment, so if you go to assignments and you see the toy compiler assignment. I've put the project description here on the web page. It'll tell you the grading scheme. It'll give you instructions for cloning it and submitting it. There are instructions for testing your compiler, instructions for submitting the compiler, some example input and output, and how to run it and everything. So you can look over this. It should have enough information as a reference for everything you need for this project. But let me walk through what this looks like. Okay, so just like with the Git sandbox, you click on this link, and it will ask you if you want to accept this assignment. You click accept, and then you should, if you refresh, you should get a link to your repository. So here's my repository on GitHub. Assuming you've set up Git with your SSH key and Vagrant and done all that from last time, you should just be able to take the git at GitHub address copy it, and then in your virtual machine, git clone, the link to your repository, and if your SSH keys are all set up, you should see something like this. And now you've got a folder here with the same name as your repository. So it should be called toy-compiler-1- and then your GitHub username. Okay, so change directory into there, and now you're in your toy compiler. So if you try to build and run this, it'll break because there's no C files yet. But once you have this written, you should just be able to type make. It'll compile, and you'll get this program called toy. Let me show you how to run this. Oops. So I'm using a little command line tricks here to accomplish this, but basically what it'll look like when you run it. So I have this example toy. I have this example toy program here. That's what the example program looks like. And I use pipe, like we talked about last time. This will just take the output of the cat command, the set of these, this toy program input, and it'll pipe it to the input to my compiler. So do /toy to execute it in the on a use command line. And it gives me this assembly code output. So you can see for each of these 4 instructions, I've got the move instruction, the add, and then setting up the call to printf. So each one of these instructions, like 1 + 5, creates an assembly code block. So that's what you should get if you run your compiler this way. So you can look at the notes, the lecture notes from class to see how to actually run it. Okay, so there's some extra stuff on here. There's this template start and all this other mess on the screen. Let me walk through what all that does. So what I'm doing is, I'm running the cat command, and I'm taking these 3 files. One is template start.s, the output of running the toy compiler, and template end. And this just contains all the code to make a complete assembly program. So let me show you what that looks like. So I've got this. I basically just have some template assembly code. So this just sets up the assembly file. It creates the main function and does the setup for the main function. And the template end just finishes the main function and adds some debugging code. So you don't have to worry too much about that. That's just assembly setup. But our goal is to take that template start, the output of our compiler, and then the template end, and make that one assembly file. And I'm just using a little command line kung fu here to have this all work in one command. So you can just copy it, and it should work for you in the virtual machine. But just to explain a little bit what this is doing, this little esoteric syntax here is running this command, saving the output to a file, and then replacing this with the output of a file. It's a way to just create a temporary file on demand without having to save it to the file system. So it's the same thing as if I had template start, but I run a command to create the file. And then at the end I put template end. And if I show you the output of this, it's going to contain, this is all the text from template start. This is all the text from our compiler output. And then at the bottom is the text from template end. So don't worry too much about that. You can just copy the command and use it. So that gives us our full assembly program with our templates and the output of our toy compiler. And I'm going to let me save that to example.s. So this is now a file that contains our complete assembly program that we generated with our compiler. You can compile it just like you would any C or assembly file like this. So just run GCC. I'm going to give it the file a name, the output file a name. But we're compiling our .s program, so GCC will also run the assembler for you. And now I've got this example program. Yeah, question.
Here we go. Based on the homework, it says handwrite all the source code using the images in Discover repository.
Right.
How would we access the images? Because I can't open the images in VirtualBox.
Oh, that's a good question. So you can either open it on your host machine or just view it in GitHub. You can view it in GitHub, yeah. Yeah, if you view it in GitHub, it'll show you the images.
Okay, so we can do that. Thank you, Serge.
Sure. All right, so we've compiled our example program here. And now let's run it. And recall the input. Recall the input was this set of 4 instructions. And then when we run the program that we generated with our compiler, it gives us what I hope are the correct answers. So 6, 3, 24, 2 in integer division. Okay, so that's how you can use your compiler, generate a working program, and actually run that program after you've generated it with your compiler. Questions about this process? Yeah. Oh, I thought you had a question, sorry. Questions? So this is all documented in the project overview here. So it'll walk you through the commands you need to run. So this shows you all the commands. Oh yeah, so if you want to, while you're developing it, you might have a bug or you want to make sure that your output is correct. So you can run this command to check whether your output is correct. What does diffw do? Oh, okay. All right, yeah, so this is, in your version of the compiler, you should have this expected. I've given you the expected output, I believe. So my output program is the same, but if, say, you missed say you messed up the subtract instruction or something, then this is the output you'd see. If you were missing something or something were different in your output from the expected output, this is what you see. Yeah?
So when developing this code, VS Code or something like that, do we have clone the repos or normal desktop and then pull it from?
You have a couple of options. You could either clone it to your /vagrant folder, which is, for most of you, is mapped to your host machine, and then do your development there. In the folder, so on your host machine, the folder where you put the vagrant file will be mapped to /vagrant on your guest machine. So you could do development there, or yeah, you could clone it on both your host machine and on Vagrant, and then use Git to move it back and forth. So depending on what your machine you're on, you may not get the same. Yeah, the reason I use the virtual machine is to make sure everybody has the same platform. So if you're not on an Intel machine, you may not have the tools to compile for Intel. Yeah. So, but yeah, you can do either. You can do either. Yeah. So you're saying. You're saying here in the expected output, like this stuff? Probably not. I mean, it's just text. Probably could have left it out of the template. I doubt it's going to cause any issues. I mean, this works on the Vagrant virtual machine, so as long as you're compiling it there, it should just work. Yeah.
Also, it says we have to handwrite all of the PNGs.
Yeah.
So how would we do that? Just like write them on a piece of paper, take a picture.
Oh, so no, like type them in, hand type them in. Yeah, yeah. So let me go through that process as well. So what that looks like. All right, so let me go through the code, and then I'll actually start like implementing what I've asked you guys to do. I'll start doing that process. Let's see. I'll go through on GitHub. Actually, no. Let me do this in Emacs. Okay, so here's my directory listing after cloning the repository. So the entry point to this program is in main.c. And this is all this program does. It gets the first token in the input by calling the Lexer. It then calls the parser and saves the root of the tree, and then passes the tree to the code generator. So those are each of the kind of three phases of our compiler. So we're not doing intermediate code, we're not doing type checking. These are the three phases of our toy compiler: lexing, parsing, and then generating code. And these are the header files for each of the three phases of your compiler. So let me go over the API real quick. So you don't have to worry so much about the data structure. So I've got functions that will create all these data structures for you. But this is the interface to the Lexer. This is the interface to the parser. So we've got this parse statement list function is what we called. And then we have the interface to the code generator. So just like in the lecture notes, there's one generator for each parse tree. So let's look at the implementation of the Lexer. So for each of those API calls, the lex function, I think I've given you Lexer error, and each of the create nodes. This is what the program looks like already completed. So when you're doing your homework assignment, what you'll do is you'll pick one of the C files to implement. It'll give you an image that has the source code. It'll give you an image with the source code. And all you need to do is create a new file in your own repository. So this is lexer.c, and just hand type. So that's what I meant by hand write. Hand type the Lexer.
Create our own file in the
Yeah, we'll create your own file in the repository. So yeah, let me show you what that looks like. So let's say, okay. So let me show how to submit and actually we do this. So let's say I actually finished hand writing the Lexer. So here I've typed it all out very quickly. Let me go back to the template here. So I've created this new file, lexer.c. here, I looked at this image and I created Lexer.c from here. So if you run git status, it'll show you that you've got a new file. So you can add that file using git add Lexer.c. And you can commit that file with commit. So the text editor will come up, and I can just make a commit message here that says I've added Lexer.c. And in order to actually submit that, push that to the repository, do git push. So let me show you what this will look like on GitHub. So right now on GitHub, I only have lexer.c.png. So once you add that file, commit it, now your local repository, if you run git status, you'll see there's nothing left to push, and it'll tell you that your copy of the repository, your branch, is one commit ahead of master. So you can see here, this is the last commit that GitHub knows about. You can see origin master is GitHub's copy. And this is the commit that we've added. If we look on GitHub, you can actually see their commit log by clicking on this little time thing. So you can see all they have is this initial commit. Once I push, that will synchronize your copy of the repository with GitHub's copy. So you should see something like this, where it's mapping the two commits, the new commit to GitHub. If I go back to GitHub and refresh the log, you'll see I've got this new commit log entry that I made on my local machine. If you look at the code, you'll see here's my new file, and it tells you when it was committed. Make sense? So once we've got everything implemented, so I'll just pretend I've implemented everything by copying all the C files here. Oops. And commit them all, including main. What happened? So if you want to see what's about to be committed, you can look here. So I finished project. Then you can push it and see that all of the files have been added here. So parser.c, main.c, lexer.c. Yeah, what was your question?
So we create all of this in the same file as the toy compiler did?
Yeah, the same directory. You put the same directory that you cloned. So this is the directory you should be doing this in. So if you've cloned your repository by its name, toy compiler 1, and then your username, this is where you're going to do all of your development work. Create new files, edit files, and that's where you'll do add, commit, push. Yeah.
So you can pretty much do all the work in the host machine, but we just have to test it.
Yeah, you should test it in the virtual machine if you don't have an x86 machine with yeah.
We're gonna have the PNG files, and then after we copy everything over with the C files, then that's pretty much it.
Yeah, the PNG files will still be there. They're not being used for anything. Yeah. So just follow those. Oh, I forgot the header files too. So then I copied over the header files. Then you can just follow the directions for, building and testing your, something didn't work. So I guess I broke something. Well, anyway, you can follow the directions that I just showed for building and running your toy compiler. Yeah.
Is there a way to also use
I don't know if it has X windows on it. I mean, there is a way to do virtualization and have the windowing on it. But yeah, because it's only text-based, I think it's headless, unless somebody tried opening up the window. Yeah, there wouldn't be a way to run graphical stuff on the virtual machine. There may be a way to connect remote. Yeah, I don't know. I think you can use GitHub to communicate between, or use that shared folder. The shared folder is probably the easiest way to do it. So when I don't think I have my virtual machine up. But when you run Vagrant up, it's going to map this folder to /Vagrant, /Vagrant on your guest machine. So if you do all of your cloning there, then you'll be able to do your editing on your Windows machine, and then do your compilation and testing on the guest machine. So once that loads up, I'll show what that looks like. Oh, I think it is loaded. So actually, you can see here. Here's where it mapped. In the guest machine, it mapped /Vagrant to my host machine. This is my current folder on my host machine. So once I go into my host machine, in the /Vagrant folder, any files I create here will be visible. So this is my host machine here. Will be visible on my host machine. So one thing you can do is clone the repository in the same folder as your Vagrant file, or in the /Vagrant folder. If you're in your guest machine, clone it into the /Vagrant folder. So let me have two. The projector won't show the bottom. So let me show them side by side. So on the right, this is my this is my guest machine, Vagrant at Ubuntu. If I do all of my work in the /Vagrant folder, everything there is going to be mapped to, so this is my host machine, Paulette device. This is my guest machine, Vagrant at Ubuntu. These two folders are mapped to each other. So because I've cloned my repository in this Vagrant folder, so this is my toy compiler 1 repository, anything I do on one machine will be reflected in the other machine. So I could open my graphical editor here on my host machine. So say it's VS Code or whatever you'd like to use. So I am editing on my host machine. And then if I view that file on my guest machine, you'll see that you've edited there on your guest machine. And then on your guest machine, you can do the compilation and project submission. Make sense? Sound good? Yeah.
Is the Vagrant file always actually the same folder with the one we talked back to the guest?
It's just the way the Vagrant file is set up is to take whatever current folder you're in, that you set up the Vagrant machine, and map it there. I mean, you could map it elsewhere, but I've set it up for you that way. So yeah, and I think you need the Vagrant file there still in order to keep it. Yeah. But you could set it up in a different way. The virtual machine is not in that folder. The virtual machine is, if you're using VirtualBox, it's elsewhere. So it's not going to take up lots of space in that folder. Yeah.
Can you still do like work in the root directory and not in the Vagrant
in the guest machine? Yeah. Yeah, so you could clone here as well. I don't think I have my keys set up. But you can clone, yeah, what was asked was, can you do work in the home folder? Yeah, for sure. You can do work here and clone here. But if you want to map between the two systems, use that /vagrant folder. And I know for some of you, you're having issues with that mapping. So one workaround is to clone into the home folder. It's the tilde folder. And you can just clone separately on your host machine. You can also sync that way. You can use the Git repository itself to synchronize between your guest machine and your host machine, where each of them has its own copy. And you use GitHub as like the central repository. That's another way to synchronize. Questions? Other questions about this setup? So I think all of this is also, you can watch this video again, and also this is outlined in the instructions here. Okay. And so you'll notice on web courses, there's nothing to submit on web courses. The graders, we're just going to look at that Git repository. So we'll clone all of your repositories and just run these exact commands that we have here for testing your compiler. Just build it and run the output. Yeah.
You can only use the testing commands after you finish writing everything, right?
Yeah. It won't. Yeah. If you don't have all the C files, it won't build. And if it's not complete, then you probably won't get the same output. You won't get the right output. For your big compiler project, I've given you finished implementations of the various phases, so that if you're working on one phase and you didn't finish an earlier phase, you won't be stuck. But for this one, you have all the code. You can just handwrite it. Yeah. Yeah, we'll look at the latest commit. I can't remember if we blocked. I mean, we'll look at the commit on the date, the due date, basically. So the Git will actually give us, it'll time you basically. You can't commit it after the date. I mean, you can, but we have the log, the time log. Other questions about this process? So I mean, this is another reason why I want to do this assignment, because this is how we'll submit the main compiler project, and I want to make sure all the kinks, all the issues are out of the way now, so that when we get there, everyone's all set up. You got your whole system software set up, your development environment, and hopefully it'll run smoothly. Yeah.
So how exactly will we end up submitting it?
As soon as you push, as soon as you run push, you've submitted it. So when I ran push, and you go and looked on my repository, if you look in the history here, you can see that all of the commits that you made on your local machine after you run push, they're all synchronized to GitHub. So that's your submission. Just by using version control, by having it synchronized with GitHub, that's for us, that's our grading repository that we're going to use for grading. So if you've pushed there, and you can confirm this by recloning your repository somewhere else and trying to rerun it again. Or just looking on GitHub and making sure that, say codegen.c, well, this is what I wrote. And it even has the date. So it says 10 minutes ago, it has the date. You can look at the commit log, and you can verify that you submitted everything. In your repository, if you type git status, it'll tell you whether there's anything you haven't committed yet. Just to make sure, maybe you implemented it, but you didn't sync it to push it to GitHub, or you forgot to commit. Git status will tell you if there's anything missing. So I also like having this version control, because this is if you're a professional software developer, you'll be using version control, and knowing how to use it is useful. Yeah. I'm sorry, a second. The input language? The input language is just this. So as an example, the input language is this set of arithmetic expressions. Defining it a little more explicitly, this is the syntax of the input. So that's the input language. It's just a list of arithmetic expressions, just a list of single arithmetic expressions, number, operator, number, semicolon. And that's it. That's the input of the compiler. Other questions about this? So yeah, feel free to reach out, or definitely reach out on ed discussions if you have issues with submitting or committing. You can always kind of hand verify yourself by looking at your repository. You can make sure, you can look at the time of the last commit, you can look at the actual commits, you can look inside the commit and see what was changed. So you can see here it's clear that I added these files. So yeah, version control gives you the way to kind of manage your own software and make sure that you don't have, if you're just trying to copy entire directories, having shared directories and making changes, you're not sure what's been fixed, what's been broken, version control helps solve those problems. Yeah. No, we'll just look at the most recent before on the deadline. We'll look at the most recent on the deadline. And for this, for the full compiler, you'll be able to resubmit as much as you like, which just means you just keep pushing. And then you can just let our graders know, and they'll just, not immediately, but maybe every week, they'll regrade whoever would like to be regraded. And so, yeah, it makes it easy for us too, because you just sync your code here, like it's a professional software project, and then we just clone whatever the latest version is. In the past, I had like you do tags and stuff, but I've made it a little easier this time. Yeah. No, the SSH key will work in the machine that you set up. So as long as you've created for your machine, yeah, I mean you could copy the key between machines as well, but yeah, it'll work for the whole machine, not just the one repository. Other questions? This is good getting these questions out. So yeah, try it. I think I've given you 2 weeks. Well, let me make before I misspeak. Do the 9th. So yeah, I've given 2 weeks to do this. It's just hand copying. Start early just to make sure you don't have any issues. Make sure everything's Vagrant set up. You can clone, you can edit, you can commit and push. We're not going to grade it until the due date, so don't worry about having broken code in there. In the professional world, don't push broken builds, but here, it's your own repository, it's okay. Yeah, do you have a question?
I just wanted to point out in your update with college projects, part of your website, whatever, there's a small typo.
Oh.
Compiler 2 during Parser that says create your git repo using compiler 1.
Oh, thank you. This is in the instructions, right?
Yeah.
Oh, this. Right here, right?
Yeah.
Thank you. Thanks. I'll update that. Other questions, other issues, other concerns? Yeah.
How do we create all the files in the how do we create
In Vagrant?
Yeah.
So if you mean like on the command line? So there's a couple of ways. So if you have everything synced between the machines, you can just create them on your host machine in that folder, in your host machine folder, in the copy of the repository there. If you want to edit in your host machine, in your guest machine, your virtual machine, you could use one of the command line editors. So Nano is the easiest one, or the kind of most user-friendly one. And you can just create your new file there. You can just nano new file.c, and it'll bring up an editor, and you can start. editing here. It uses, so there's no mouse involved in the command line. It doesn't read mouse commands. But you can use the arrow keys. So here's my Hello World program. You can actually edit here. And then it actually gives you commands on the bottom to operate your editor. The little caret, it means control, so you hold control. Hit X for exit, save, hit enter to save it to that file. And now you've got your new file here.
Do we have to name the file something specific, or does it have to be, or can it just be, does it have to be the same name as?
Yes, yeah. So this is the name of the file already, just without the .png. So you'll create a lexer.c file corresponding to lexer.c.png.
Okay, so what about the Lexer.c file that's already there?
This one I added. So this I just created. So if I were to check out the, so to show you what this looks like when I first cloned it. This is what the repository looked like when I first cloned it. So there's no lexer.c. I added that when I was demonstrating how to do this. And so then when I did all my changes, then when I made all my changes, this is what it looked like. Yeah.
There's like using tab or space matter in Nano.
In Nano, let's see. It looks like it does recognize tabs. And we can actually use that, we can use that OD tool to show us whether we've actually got tabs or new lines. OD-C will give you the C language escape characters for non-printable characters. So we can actually see that when I hit the tab character in Nano, it created an actual ASCII code for tab. And these are the spaces. You can also do hex if you really want to see the ASCII code. And it's little endian, so these are like flipped. But yeah, good question. Yeah. Oh, we'll see that next time. So the parser that you're going to be writing today is implemented from scratch. It's a scratch implemented parser. Next time we're going to be using a tool that will automatically generate a parser for you from a grammar. So you just write the grammar, and then it'll generate a C file, C program that will parse that for you. We're going to be using that for our Simple C project. You'll actually be completing that grammar, or using that grammar in order to generate your parse tree. So next time we'll look at the generated one. Other questions? Questions? So let me actually walk through how this compiler works. So this is the Lexer. This is the Lexing function. And this function, it takes nothing, and it just reads from standard input and gives you one token at a time. So it gives you one token. My token structure looks like this. So the token is just an enum to say what kind of token it is, number operator, semicolon, end. And then it's either a C integer or a character, depending on what kind it is. So don't worry too much about that if you haven't looked at like C too much. We'll look at that more when we look at simple C. But it's just a function that you just call it once and it'll give you a token. Call it once, give you a token. Call it once, give you a token. And so here's how it implements the specification of our language, the reading of our language. So it reads in one character, fgetC just reads in a character from the standard in. And then there's just a series of if statements to check what kind of ASCII character was input. So if it's the EOF ASCII character, so that's end of file, there's a special file for end of file, then it creates the end token. If it's an ASCII digit, one of the characters from 0 through 9, so C has functions for doing this for you. You could also check the ASCII code yourself. If it's a digit, then it creates a number token and returns that. If it's a space character, I've written support for spaces. So if it's a space character, it just calls Lex again to skipping the space. If it's a semicolon character, it returns semicolon token. So pretty straightforward, right? It doesn't really do much. It just like takes the ASCII text and bundles it in this structure. But the information difference is that now our parser will know which type of token that it's looking at. It doesn't have to know about all of the digits 0 through 9. It doesn't have to know about ASCII. All it knows about is that there are only 4 different possible tokens in our language, and your parser will be easier to write and easier to specify. And then the last part just checks for the operator characters. So this is just a fancy way to say plus or minus or star or divide, using the maybe unusual pattern of using case without break. And that's it. Questions on the Lexer? So it seems almost redundant, like why would you need to do this? But this is about interfaces. You know, we talked about interfaces and abstraction a couple of weeks ago. And so designing this is not about like trying to read or write the compiler. This is about separating lexing from parsing, so that the parser doesn't have to worry about ASCII, doesn't have to worry about the file, doesn't have to worry about individual digits. The Lexer provides an interface that separates the parsing process from figuring out which kind of token you have in your input program. Questions about the lexing algorithm? Okay, so here's the parser. The parser is a little bit more involved. So there are only 3 parsing functions. So recall that our language only has a list of statements, a statement, and an expression. So I've written in comments above each of these functions a little notation that describes what this parsing function is doing. So starting from the expression parser is just saying, if I see number followed by operator followed by number, then I've seen an expression. So the parser is looking at the individual tokens in the input and trying to figure out which grammar construct the user has given us. So in the toy compiler, there's like not a lot of grammar constructs. But if this were, say, the C language, we might see X followed by star followed by Y. And the parser's job is to figure out whether that star is a multiply operation or maybe a pointer reference. If it sees minus, it needs to figure out whether that's doing a negation or whether that's doing subtraction. If it sees an if symbol, and then it sees curly braces and sees a while symbol, it has to figure out what construct the user is writing to the compiler. And this little comment is a way of describing, specifying what each of these grammar constructs are. So in our toy language, an expression grammar construct is always a token, a number token, followed by an operator token, followed by a number token. And while we could probably write some giant parse function in a for loop, I've broken this down so that each construct in our language, statement list, statement, and expression, has its own function that is responsible for recognizing it. So again, it's about simplifying the problem, breaking down the specification of the problem. So that's what parse expression does. And the way it's implemented is pretty simplistic. It just gets one character from the Lexer. So get look ahead will call the Lexer to give it one character. And it'll just check, is the next character a number token? If it's not a number token, then there's an error. The parser was expecting that there was going to be number followed by operator followed by number. If it doesn't see that, then it's not a valid input. Otherwise, it moves on and gets the next token. Then it collects the next token, checks whether it is an operator, which is what's the definition of our language, it's number followed by operator followed by number. And if it is, we're all good, we move on. And so on. Gets the next token, checks whether it's a number token. If it isn't, it's an error. If it is, we move on. And then the final step is actually constructing the parse tree. So once the parser recognizes that we've seen number, operator, number, we know we've seen a valid expression statement, and we can construct the parse tree. So to look at that in a diagram, if we've seen if we see this in our input, so it doesn't matter what actual numbers and operators we used, the Lexer here is defining this interface that will take our raw ASCII characters and turn it into just abstract token names, token types. So this is what our Lexer does for us. And then the parser, when it sees this sequence of tokens, it'll construct for us a tree structure that records the contents of that expression. So we've gone from raw ASCII code, which has no structure to it, which has no meaning. We've turned it into a sequence of tokens, which tell the type of token in our language. And the parser identifies what programming language construct has been given to us by the user. Kind of make sense? Questions on this? So that's what the expression parser does. That's all it does. And now the statement parser function. A statement, if you remember informally, was just an expression followed by a semicolon. Just like in C, a statement might be an assignment followed by a semicolon. So in our toy compiler language, this is the grammar specification of a statement. It's just expression followed by semicolon. And so just like the expression parser, what this function is going to do is it's going to check to make sure the input indeed is an expression followed by a semicolon. And then it's going to construct a parse tree node to record what grammar construct we saw in the input. So now notice a little difference here, that in this expression, the expression was comprised entirely of tokens. There was just tokens, like raw information from the Lexer. Here, though, a statement refers to another grammar construct, not a token. So in order for our parser to check whether an entire grammar construct has been seen, all it does is it calls the function that recognizes and parses that grammar construct. See what I'm saying? So if this were like reading English language, it would be like noun, verb, noun. And you could imagine just dispatching the recognition of noun to another function, parse noun. It's the same thing here. So we just dispatch the recognition and parsing of expression to the parse expression function, which we've already written conveniently. And because that function already checks whether it's a valid expression, there's nothing more to do. We just call parse expression and depend on it to make sure that we've seen a valid expression. So this gets into kind of recursive algorithm design. When you write a recursive algorithm, you call the function assuming it's written already correctly. But we'll talk about that more when we get into parsing. And then because the next symbol that we're looking for in our input is semicolon, we do the same thing that we did for parse expression. We poll the Lexer to look at what token it's on, and just check, is it a semicolon? If it's not, we have a parse error. We saw some input that we didn't expect. It's not part of our language. And if it is, we're good. We just move on to the next part of the input, and we can now create our parse tree for the statement construct. Questions on this before? So it looks almost like why are you doing this? But what it's doing is it's verifying that the input matches the input specification of our language. So, one of your colleagues asked, what's the input to our program? This is actually defining the input by enforcing rules that check what symbols are you supposed to see in the input and in what order they're supposed to be in. So if we go back to our test input, once we see semicolon here, the Lexer turns that into a token, and the parse statement function will create a new statement node that has expression and semicolon, exactly matching the grammar specification of our toy compiler input. Start to kind of make sense a little bit? And finally, we have our statement list parser. This one's a little bit more subtle. So this is how you can encode a list structure in a grammar specification. So just like a linked list where you have head and, or actually it's like just like a linked list where you have the contents followed by a pointer to the next element in the list. This is a way using grammars to specify basically a linked list. So you can imagine that statement is a pointer to the contents of our linked list node, and statement list is a pointer to the next node in our linked list. But we want our input to allow for any number of statement nodes. So we don't want to fix the number of statements we have in our language. Like an expression, there's a finite number of tokens that make up an expression. But a statement list can have any number of statements in it. So the way we do this is we say that a statement list is either a statement followed by another statement list, which can have any number of nodes in it, or it's the end token. So by allowing for two possibilities for the statement list, we can encode any number of statements. So this recognition function is either it's gonna check to make sure, is my statement list the end token, or is it a statement followed by another statement list? Sort of makes sense a little bit? When we talk about grammars, we'll see how this actually works when you generate the parser. But let's see what this looks like in our toy compiler implementation. So we use an if statement to differentiate between the two possibilities of a statement list. So if it's an end token, then we know we've seen this variation of the statement list grammar construct. And if we haven't seen it, then we need to check whether we've seen a statement followed by another statement list. Okay, so this is, so I've checked whether end does not equal the next token. So if it is, then we just return null. If end isn't the next token, then we guess that it must be a statement. And just like when we parsed the statement, we already have a function written that will parse and check a statement for us. So we just call that function. We call parse statement. And if it successfully finishes, it will give us a statement node. If it doesn't, then it'll throw a parsing error. And we do the same thing for statement list. As long as statement list is implemented correctly, if we want to check whether the next part of the input is a statement list, we just recursively call parse statement list. And just like when you're doing factorial in a recursive way or doing merge sort, it's a little mind-bending to have to think about recursion. But if you think of it this way as just assuming that parse statement list is written correctly, and in this case, parse statement list written correctly means you give it an input program and it gives you a parse tree for the statement list. You can just call it. Even in its own function, you can call it recursively. And as long as it is implemented the way you specified it, then you'll get a correct program. So just like with parse statement, we just literally call parse statement and parse statement list to check whether we've seen a statement followed by a statement list and give us the parse tree for the statement list. And once we've done that, we can create a new parse tree node that contains the statement and the statement list. Okay, so questions on this code before I show the example. Yeah.
So, so this like view of working with the statement was basically just use the current statement, first statement in isolation, and everything else in the statement was just sort of pushed off, kind of like
Yeah, you just call a function recursively to start reading another statement if you need. So let me show what this looks like in our example. So we've got an EOF token in the input. The Lexer turns this into an N token. And so if I see an N token in the input, what grammar construct gets matched by an N token? Gets recognized by an N token? Did I hear an answer? Well, so this is the N token. We've already read the semicolon. We've already read the oh, sorry, we didn't read. Oh yeah, the semicolon. I just made it very ugly here. So we've read the semicolon and we've constructed a statement from the semicolon. But if we have an N token, if we have an N token, you can see that a statement list can be comprised of an N token. So, this keeps disconnecting. Apologies. So this N token, according to this grammar specification here, a statement list can just be a single N token by itself. I will switch this for next time. Okay, so we've seen an N token, which is recognized by a statement list. A statement list will recognize an N token, which is seen by this if statement. And now what we have left to parse is we see a statement. Oh my God, why is this? This is very buggy. Now we see a statement followed by statement lists. Which grammar construct recognizes a statement list followed by a statement? The statement list. A statement list, a valid statement list is a statement followed by a statement, another statement list, or it's just an end token. So this statement list function So this statement list function will create a new node that captures the statement and another statement list. And if we had even more statements in our language, this parse tree would keep constructing new statement lists that contain a single statement and then a statement list. Just like a linked list. And linked lists also use recursion to iterate through them. And when you write the recursion, you check, am I on the end node or not? If I'm not on the end node, go to the next node. And so this parsing function is basically just the same thing as a linked list. And we can actually, because of this linked list-like behavior, even though our input languages, our input program may be as long as you want, maybe infinitely long, maybe millions of statements, our definition of the input language is finite. This definition of statement list can capture 0 or infinite number of statements. So we can represent an infinite possible set of input programs with a finite specification of that. Yeah?
Wouldn't you run problems with the call stack when you see so many recursive call speeds?
Yeah, so the point that your colleague is making is that because this is using recursion to do this, your call stack uses memory, and if you have a finite amount of memory, then you may get, stack out of stack space. So this is the kind of difference between the paper mathematical specification of a language and the physical implementation machine. So in the kind of theory of computation world, RAM is infinite in the computation world. The Turing machine assumes an infinite amount of tape. Technically speaking, a machine with a fixed amount of RAM has a finite amount of state and is not actually a Turing machine. But we use these models because trying to do everything with finite state machines is much harder. So for instance, if we wanted to use a finite state machine for this to get a little into discrete, we'd need to have a rule for each level of nesting or each number of nodes that we want to allow in our language. This allows us a really compact way. Assuming that we have an infinite amount of input, you can also use that for a finite amount of input. You see what I mean? So if our specification supports an infinite number of input, it'll also work for a finite amount of input as well. But yeah, you would eventually you would run out of space if you had, enough input. But I guess you could add more RAM to your machine, or page it out onto your disk. You'd have to fill up, terabytes of space before you get to your stack. But yeah, interesting. Yeah, good question. Questions on this so far? Okay, so that's how the parser works. We start with parse statement list, and then it says, well, I know I must see a statement next. And once it parses that, it says, well, I have to see a statement list next. And the parsing of statement is abstracted away into the parse statement function. It doesn't have to know anything about lists. All it knows is that I need to parse a statement. And for me, a statement is just an expression followed by a semicolon. So I'm just going to look for an expression and then look for a semicolon. But it passes the buck down to the expression function because we've created one function for each grammar construct and says, all right, I'm just going to ask expression to do this. An expression knows that it's a number followed by an operator for a number. And eventually we're going to reach the actual tokens of the input to the program. So this parsing process will eventually stop with some finite input. All right, so let's see how code generation works. Questions on parsing? So this will give you a little entree into parsing techniques when you hand copy this, and when you run it and you think about how it actually works. Hopefully it'll help you understand a little bit what we're going to do next time. Okay, so now that we've got this parse tree, and this is the beauty of separating the compiler out into these separate phases, is that now we have this parse tree that records each grammar construct that we've seen in our input language. We don't just have to, when we do our code generation, we don't have to try to come up with some bespoke algorithm that's going to work on this particular set of inputs or try to handle all the ASCII. Instead, we can use our parse tree to help us know what assembly to generate for each parse tree node. Okay, so let's again start at the bottom and look at gen code expression. So whenever we see an expression, we know that we're going to generate two move statements, some assembly instruction for add, subtract, multiply, and then generate the code for doing printing. So here's how we print out, so we've got this tree here. So when we're on an expression, because we have this fixed tree structure, we know exactly where to find the first operand, the left operand, and the operator. We can just look at our tree structure to get that information out from the input program. So no dealing with ASCII, no dealing with reading characters one by one. We have this tree structure that gives us all the information we need about the expression. And so in order to generate the instruction that takes the value and puts it into a register, we can just use this little template here that always moves whatever the information we get from the tree about the left operand is into EAX. The second one just moves second operand into EBX. So reflecting exactly the example output that we had. Does this kind of make sense? This is a little template for what an expression is in assembly code. And then because we know there's only 4 possible characters and we know exactly where to find that character, we can make a switch case statement that will generate a different instruction for each operator that we saw in the input. So if it's a plus, we generate add, minus generates subtract, multiply, division takes 2 instructions on an Intel assembly. And then the last code is just the same every time we have an expression. It just copies whatever the resulting value from EAX is into a register and calls print. And that's it, yeah.
Could you explain the divide, like why you're only one, like operand?
This is the design of the Intel architecture. I guess because it captures both captures the remainder and the amount. Maybe they wanted to like make it really optimal and have it fixed. It's fixed to specific registers. There's specific registers associated with the divide, I think. I'm assuming maybe they wanted to have one divide operation that didn't work with all registers. I actually don't know. I don't know. That's a good question. If you find out, let me know. You can let people know in that discussion. But that's how you do divide in Intel assembly. But yeah, so with this tree, we just traverse it. Yeah, go ahead.
If you want to make I think for interpreter like Python,
Yeah.
execute, like,
That's a good question, yeah. So for interpreting, so the difference between an interpreter and a compiler is all the first process is identical. In an interpreter, all you would do is, instead of generating assembly code, you just get the numbers of the left and right operands. And in here, instead of printing an add instruction, you just do the C like add operation. This would just be result equals expression operand 1 number plus this is how you would write an interpreter version of this, and then save that, print that result out. But yeah, that's a good question. So compiler and interpreters are closely linked. Okay, so whenever we see an expression node on our tree, this is what we do, we print it out. And because we don't really have any other constructs that create assembly language content, the statement and statement list code generators are just basically iterating over the tree for us. So the semicolon has no meaning in assembly. It's just syntax to help the compiler recognize individual statements. And so all GenCode statement list does is it just traverses the tree. This is doing is traversing the tree. It's recursively calling GenCode statement on the statement node, and then it's just recursively calling the, actually, sorry, I wrote this with a while loop, but you could do this with recursion as well. But it's just iterating over the list, just as a linked list. And GenCode statement does nothing but call the code generator for GenCode expression. When we get to our real compiler, we'll see that there are other kinds of statements like if statements and while loops, where the statement code generator will do more, will add more code. But because there's no assembly corresponding to the semicolon or statement, besides just generating the statement, it just passes through flow of control to the expression, and then calls GenCode expression. Questions on this? So pretty straightforward, right? Sort of, more or less. So just to quickly show what this looks like in our tree, we'll call GenCode on the root of our node. It will recursively call, or it'll call the GenCode for statement. GenCode for statement will call GenCode for expression. And that GenCode for expression template will be run. It'll just generate that assembly we showed earlier. It'll generate this assembly code template using the information from the tree. And once that's finished, it will return to the statement function, which will return to statement list, which will move on to the next statement list. In this case, we have no more statements, but if there were more statements here, it would go to the next statement, go to the next code generated for the next expression, print out the assembly code for the next expression afterwards, and so on until we've exhausted the entire tree. And that's it. That's the kind of core of all a compiler really does. It finds the syntactic structure of the input. It maps each construct to some assembly code template, and then traverses the tree, spitting out assembly code for each construct. The tricky part is how to design that in such a way that the output assembly actually matches the input program that actually has the semantics of it. We'll go into that more when we get into our bigger compiler. But that's how this toy compiler works. And so your job is to just hand copy this code for yourself in your own repository and just get it working so that you can say, I've written a compiler and it generates assembly and it actually runs on my machine. All right, questions? This one's also, questions? All right, thanks everyone. Have a good weekend and see you next week.